Hello, this is Mr. Henry, and welcome to Lesson 3.1, Dilations. The essential question says, how do I identify dilations? So for the warm-up I have here, give a brief summary about what you remember about the properties of rotations, reflections, and translations. So you may remember that rotations are when you have an object, so I'm going to draw like a right triangle, something that's not symmetrical. And if you take that object and you rotate it around a point, that would be a rotation. And you can keep rotating to various degrees. You can rotate around different points. Here I'm rotating around a point, this little vertex here, so it's been rotated. But you could also rotate around other points. I could rotate around the right angle. So I rotate it like that. That would still be a rotation. So that's what a rotation does. It rotates. It's a turn. A reflection is when you take the original image and you reflect it, like a mirror image. So flip left, right. That would be a reflection across something that would be sort of like a that'll work, I guess. I meant to do a line. So reflected across like an axis like this. You can also rotate across different axes. If we make, say, for example, an x-axis, we can take this and we can rotate it that way. So we gotta flip left, right, flip up, down. There we go. So that would be a reflection across something like an x-axis. And the final type of translation we talked, or transformation we talked about, was the translation. And a translation is when you have the original image and you just move it to another location. So this was translated to the right, translated up and right, to the bottom left, to top right, or top left. Okay. You might have also remembered properties like the angles are always the same. From a pre-image to the image, the angles are the same. The lengths of the sides are all the same, because these two images are just like clones of each other or twins of each other. Even though they may not be facing the same direction, they might be turned, they might be rotated, they're still the same exact image. Okay? In today's lesson we're talking about dilations. So we'll start here. A dilation is a rule that moves points in a plane a specific distance, determined by the scale factor r from a center O. It doesn't make much sense now. It'll make more sense when we start seeing some examples, but for now, just copy it down. And the similar figure, well, the similar figure is what a dilation makes. A similar figure are two figures that are proportional to one another. So the act of doing a dilation on one figure makes a similar proportional figure. So let's get a couple examples of recognizing if something is a dilation. So I have some images here. So this first one, I would like to know, is this first image a dilation? And the answer is yes. And here's how you could figure this out. In the technology age we live in, if you would imagine taking the smaller image, the first one, this guy here, and you would kind of pinch and zoom, you would get something that looks like this, where it's the same shape, it's not distorted, it's not made extra wide or extra fat or extra tall, it's the same shape, just made bigger. Another cool trick I want to show you here is if you take and you connect the points. So I connected the bottom point and the bottom point, and I'm connecting all these corresponding points. Notice what's happening. All of these corresponding points, if I connect them together, all seem to be going to some one location. That one place that they're all heading to would actually be that center point O, from that center O, that is where the dilation would be taking place. From that point, it's zooming out a certain distance. Here in letter B, so I have my internal shape here and the external shape here. They're both pentagons. So could this be a dilation? The answer is yes, it could be. And again, if I would take and connect all these lines, you see that they are all converging at this bottom corner. Because this bottom corner right here, that is that point O. That's the point of dilation. So all the zooming, the making larger and making smaller, is happening from here, zooming in and zooming out. So this is a dilation. This is a dilation. Letter C. Is this a dilation? Could we get from one image to the other image by doing a zoom in or a zoom out? The answer is yes. And again, if I connect my lines, we have a central location. That point right there would be this point O, the center of the dilation, where everything is being zoomed in and zoomed out from. Okay, what about point D, or this image in D? Could these images be the result of a zooming in or a zooming out? The answer would be no. Those images are different. This one here, it's the same width as this, but it's just made flatter. Well, you can't get that by doing like a pinch and zoom, by zooming in or zooming out. That's not the result of a dilation. So this is no. Okay? Letter E. Well, those images look to be the same. I would say, yeah, as far as I can tell, that looks like a dilation. And if I connect points, from edge to edge, edge to edge, I get a point somewhere in that ballpark. That would be my center point, O, where the dilation took place from. Okay. What about this letter F? This is a parabola. It comes if you graph the function f of x equals x squared, or y equals x squared. So, is this the result of a dilation? The two shapes don't look the same. I mean, if I pinched and zoom, I don't know if I could get from one to the other. This outside one looks wider than the inside one. But the answer here is actually a yes. This is a dilation. And the way you would get a dilation like this is if your center point is about here. Because the dilation, what it does is it increases the distance from the original image to the new image. So if I started here, that distance, and I double it, I would get here. This distance, if you double it, you get here. And the same thing, from that distance, double it, there. And if you continue straight and double it, you get up there. I'm like doubling the image each time. So that might have a scale factor of something like 2 or something. But that shows that this is actually a dilation. Now, my center point here may not actually be on the right location because this distance and that distance doesn't look to be double. But if you do it properly, it should be. Okay? So the answer here is a yes, but it's kind of a fuzzy yes. We don't quite understand why. But it is yes. It is a dilation. For the most part, the images you're going to see are probably more like these, where they're pretty obvious if it is or is not a dilation. Example 2. Now what we're going to do here is we're going to be making a dilation. The directions say, make the desired dilation about point O, so there's my center point, with a scale factor of R. And I tell you here what the scale factors are. R equals 2, R equals 1/3, and we have letters C and D as well. So let's see here. Dilate ABCO with a scale factor of 2. Now, what that scale factor means, that means that every distance, so the distance from A to O, needs to be 2 times, twice as big. So if OA is 1, 2, 3, 4, 5, 6, then OA prime, the new point out here someplace, needs to be double that, or 12 units long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the same thing here. From OC is 4. So if I double that, 4, 5, 6, 7, 8. Now, I'm going to use, well, I'm going to try to make this as pretty as possible. That's terrible. Let's try that again. How about this? I've got a line tool. Let's use that. Make it blue. Get another line. Make it blue. So there's OA prime, the new location of the A value in our image, and there's OC prime. And since it's a rectangle, all I'd have to do is just extend this guy, extend that guy, and we now have, when we've R equals 2, that's our new image when our R value is 2. I'm not going to put down the A prime, B prime, C prime, simply because we're going to be putting 4 different images in this same picture, and if we put the A, B, C primes, it's going to start getting pretty jumbled, and I want to keep it as clean as possible. So I'm just going to put down that this came from the scale factor of 2. Alright, letter B. Dilate ABCO, the scale factor of 1/3. Alright, so I'm going to take each side length of my original image and multiply it by 1/3. So if my OA is 6, then OA prime would be, well, 6 times by 1/3, calculator, 6 times by 1/3, and then you get 2. So my new length of this point will be here. And the other side, OC is 4, so OC prime would be this 4 times by 1/3, which is, clear, 4 times 1/3. And then fraction of decimal best we can, that gives us about 1.3. So 1.3 would be someplace in here. There we go. So this is our new image from this OCBA if we use a scale factor of 1/3. So this is R equals what? 1/3. That was ugly. Let's try that again. Now put it inside. R equals 1/3. There we go. So this is our scale factor. Now don't draw this line that I'm about to put here, but I wanted to show you if I extend, look at this. They all these B's go right to this same line. These are all proportional images. They're all similar to one another. Now, on the next slide here, I don't have these 2 original images down, but I have 2 more that I'd like you to make. So for letter C, please dilate this ABCO with a scale factor of 1/2, and then again with a scale factor of 3/2. So pause the video, try it right now. When you unpause the video, I'm going to have the other 2 images back up here. Alright? Alright, so I've copied the other image back onto this page. So now let's dilate with a scale factor of R equals 1/2. So I'm going to take all of these lengths from OA. So OA is still 6, so OA prime would be 6 times by the scale factor, which gives me 3. So here. And then OC is 4. So OC prime would be that 4 times by the scale factor gives me 2. 1, 2. So I get a rectangle that looks like this. This is R equals 1/2. So this image here is half the size of that image here. Or I should say each side is half the same size as the original. Letter D, dilate ABCO with a scale factor of 3/2. Okay, let's see. OA is 6, so OA prime would be 6 times by 3/2. And if you can't do that in your head, we've got calculators for it. 6 times by 3/2, and decimal that gives us 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be our A prime for this letter D. And OC is 4. OC prime would be 4 times by 3/2, which is going to give us 6. But you don't trust me. 4 times by 3/2. Got 6. So 1, 2, 3, 4, 5, 6. And I'll jump back to my line tool here. There we go. And that came from R equals 3/2. By the way, in case you're curious what a scale factor of like 1 would look like, a scale factor of 1 is the original image. So look what I have here. If I do the same experiment again, look, if I connect this O through all these points, all these B primes and B's go through this same diagonal. And if you have any rectangle that would go through this same diagonal, they would all be proportional. They're all just dilations of one another. Now, the next slide has a question that relates to this picture, and I'll pull the picture back up here in a second. But the next slide says, what do you notice about the relationship? What do you notice about the dilation factor and what happens to the new shape? Or the relationship between the dilation scale factor and the image we got? Do you notice a pattern? Put down your answer. I'll leave this image up here. What do you notice about the relationship between the scale factor and the new image? So maybe what you noticed is, well, the bigger the scale factor, the bigger the new image, which would absolutely be true, because if I have a scale factor of 3, I'm going to take this distance of 6 and I would times it by 3, and my new distance would be 18. Be huge. And same thing along this side. 4 times by 3 would be 12. And I can go higher. I can go scale factors of 10 and 20 and 30 and whatever else. So big scale factors make big images. A small scale factor, like half, each side is half the distance. A third. Each side is a third of the distance. So the relationship, what it comes down to is, if your scale factor is bigger than 1, you get a new, bigger shape. I'll put image. It's the proper word for it. You get a new, bigger image. So this C prime, B prime, A prime is bigger than the original because I had a scale factor bigger than 1. If you have a scale factor less than 1, you get a smaller image. So half gave me a smaller image. 1/3 gave me an even smaller image. If I did 1/4 and 1/5, even smaller images. And the only other thing I want to mention here, just to make sure I'm clear, if you want the scale factor to be bigger than 0 and less than 1. Fractions. I'll be honest, I'm off the top of my head, I can't quite picture what a scale factor, a negative scale factor would be. I guess it would just be a going this direction as opposed to going this way. And a scale factor of 0 would just be a point. Each distance you take times by 0, which would be 0. So it would just be a point. So to get ourselves a new image, we typically want to stick with factors or numbers between 0, getting bigger than 0, and up. And that's kind of the property. Now, the last couple we saw were just we drew pictures, we constructed it. Let's look at a couple where it's kind of a word problem, or where a picture is not drawn for us. Letter E, for example, says, if OC is 4 centimeters and it is dilated from center O by a scale factor of 4, what would be OC prime? You may have a hard time imagining that. Draw a picture. It doesn't say what shape this is, if it's a triangle or a rectangle, so draw something simple, like, well, even maybe just a segment. OC is length 4. Now, if that is dilated from center O, there's my center, by a scale factor of 4, so everything's made 4 times longer, what would OC prime be? Well, OC prime would be 4 times that, and 4 times 4 is 16 centimeters. So our new shape, OC prime, there we go, would be 4 times that guy, which is 16 centimeters. The same thing could also be true if you used like a triangle. O, B, C, whatever. So if that's 4, and if this is your center point, which means you're going to just get longer going that direction, it would be way out here. OC prime would be 16 long. It's still 4 times as big. Here's one for you to try. If you have a segment OM of length 24 inches, and it is dilated from a center O by a scale factor of R equals 1/6, how long is the dilated segment? Go ahead, pause the video right now, try that problem on your own. When you're ready to continue, hit play, and we'll go through it together. Okie dokie, so I'm going to draw a picture. OBM, I guess, because I need OM. So this OM is 24 inches. And it says dilated from center O. Okay, so it's going to either get bigger or smaller from that point by a scale factor of 1/6. Well, since I have a small scale factor, less than 1, my new image is going to be smaller. How long is this new segment? Well, if it's 1/6 the size, 1/6 of 24, of in math almost always means multiply. 1/6 times by 24 gives us 24 times by 1/6, and fraction of decimal gives us 4. Our new segment would be 4 inches long. 4 is 1/6 of 24. Our new segment is 1/6 of the old segment. Okay, we'll do little applications here. So an engineer knows that on blueprints for a bridge, a support is 6 inches. Okay, so blueprints, got some little bridge thing, got some supports. That is 6 inches. On the actual bridge, the same support is 18 feet. Actual bridge, 18 feet. What is the scale factor from the blueprint to the actual bridge? So I need to figure out what is this scale factor to go from here to there. I'm getting bigger. All right. So the scale factor is a ratio. It's a ratio that shows the relationship between the one image to the other image. So ratio, my two possible options are either 6 inches to 18 feet or 18 feet to 6 inches. This is the one that we actually want to use. This is the ratio of the from the blueprint to the actual bridge. Because we're getting bigger, this would give me like, well, this is wrong, but this would be, if I would reduce this 18 over 6, it'd give me a ratio of like 3. No, now I know the actual bridge is not 3 times as big as the blueprint. I'm just showing you, if you would simplify this fraction, you would get 1/3. 1/3 would be, the blueprint might be like 1/3 of the actual bridge. Now, the reason why I'm saying this is not correct, because it's not, is we have these pesky labels in here that are messing us up. If I, again, would reduce this and get an answer of 3, no, this bridge is not 3 times the size of the image. This is 6 inches. This is 18 feet. That's a big difference. So what we need to do is we need to get rid of the issue of the labels. We need to make all the labels the same so we can actually start comparing these things. So if I could take and turn all my labels into inches, we could then make a comparison. So the bottom guy, well, he's already 6 inches. He's good. The top number, though, if I could turn 18 feet into inches, well, in every foot, there are 12 inches. So 18 feet would have 12 times by 18 inches. 12 times 18 equals 216 inches. So that's how long this support is in inches. It's 216 inches. So now we have an actual comparison. 216 inches to 6. If we simplify here a little bit, /6 and simplify, I get 36 over 1. So the ratio is, my bridge is 36 times as big as the blueprint. That is my scale factor. My scale factor is 36 times from here to the actual bridge. Now, you say, well, what if I did it the other way on accident and I used this one? What would I get? Well, if you do the same process, you're just going to get 1 over 36. It would not make sense if you take 6 times by 1 over 36. You're not going to get that 18 feet, that 216 inches. That 1 over 36 is actually the reverse. It's 18 feet times by 1 over 36 gives you the blueprint. So the scale factor kind of goes both ways. It tells you what to multiply by to get from the one to the other, and even the reverse. Here's one I'd like you to try. It says a scale model of a rocket is useful when testing out new technologies, as they are typically much cheaper to make. If a scale model, that should be model, if a scale model of a rocket engine is 4 feet tall, this is a dilated scale factor of 1/3. What would be the height of the full-sized rocket engine? I would recommend you draw a picture. Go ahead, pause the video, try it right now. When you're ready to continue, hit play, and we'll go through it together. Okay, so we have our little rocket engine, which is 4 feet tall. We have our big boy rocket engine, which we don't know how tall it is. That's actually what we're trying to find. So I'll call it X. Now, the problem here tells me that this scale model has a scale factor of 1/3 of that thing. So this times by 1/3 gives me my 4 feet. Right now in my head, I can think of two ways we could solve this problem. One is we can use an equation. X times by 1/3 equals 4. My missing thing times by 1/3 is 4. So if we solve this equation, we'll find our missing piece. Times both sides by 3, cancels, cancels, x equals 12 feet. That's way number 1. I'll leave it up there. Way number 2 would be, well, if this is 1/3 smaller, that would mean that this going that way is 3 times bigger. So if I take 4 times by 3, I still get 12 feet. So that is kind of two different ways you can think about the same problem. I like this one, but I can do this in my head pretty quickly. I can understand this relationship. Many students have a hard time picturing that relationship, so the equation might be better for you. And letter C here. Letter C would like us to draw a dilation of the figure to the right, now mine's below, with a scale factor of r equals 1/2 about center O. And that is this point here. This is point O. So we want to draw a dilation of that with a scale factor of 1/2. Now, there's some ways that I've thought about doing this that I think might be useful tricks. I don't know how easy they are to explain, but I'll try. So, for example, from this point O to this point, and I'm just going to label them A, B, C, just so we're talking about the same point. So, from O to C, I could use that distance formula we learned in the last module, find the distance, cut it in half, and go from there. But that's kind of a pain in the butt. So here's kind of a method I came up with, and see if you like it. So for me to get from O to C, the directions I would follow, I would go down 2, over 1, 2, 3, 4. So if I cut each of those in half, if I went down 1 and over 2, that is half the distance from O to C. I cut each of those units in half. I went down 1 over 2 instead of down 2 over 4. Same thing works for each of the points. To get to letter A, I could go over 2, down 2. Well, half of that direction, instead of going over 2 and down 2, I'd go over 1, down 1. And from O to B, over 2, up 3. Well, over 2 up 3 goes to half it would be over 1 up 1.5, because half of 3 is 1.5. So over 1 up 1.5. So I think if I connect these 3 points, that should be my new image of A prime, B prime, C prime. That last line got a little out of shape here. Oopsie, I meant to use a line tool. That. So that's A prime, B prime, C prime, dilated with a scale factor of 1/2. Don't draw this in. I'm just going to show you. Remember that trick I showed you about if you take from the center point O and you connect the corners? They should all go through the same lines. And looky here. They do. That shows you that this new image I have here is proportional to the original. So that was letter C, scaled with a factor of r equals 1/2. Each leg, each side of this triangle is half the size of the original. Look, 1, 2, 3, 4, 5, 6, 1, 2, 3. 1, 2, 3, 4, 5. Half of 5 is 2.5. And if we use the Pythagorean theorem, we could find out the length of this side, and this side would be half of it. I would like you to please do letter D. You're using the same space on your note sheet, but this time you're going to dilate this image with a scale factor of 2 about the center O. So if you could please pause the video, do this problem on your own. When you're ready to continue, hit play, and we'll go through it together. All right, so let's do it. So for me to get from here to here, so this was A, B, C, just so we're talking about the same corners. From O to A, I went over 2, down 2. Well, if you're going to be doubling that, timesing it by 2, you're going to go over 4, down 4. There's my A prime. From O to C, down 2, over 4. If you're doubling it, you're going to go down 4 over 8. 1, 2, 3, 4, 5, 6, 7, 8. There's C prime. To get to B, you can go over 2, up 3. Well, doubling that would be over 4, up 6. 1, 2, 3, 4, 5, 6. Okay, let's get rid of some of this extra gibberish in here. So there's A, B, C, and line tool. Make this nice and pretty for us. And there's my new image. And again, you don't have to draw these lines, but if I do, all my corners should match up. And would you look at that? Even my old image, if I fit it in here, was there. That's the one I used when I had a scale factor of 1/2. They all are proportional. They're all similar figures. So if you could please answer this question in the summary box of your note sheet. It says, how do you identify dilations? How do you recognize if something is a dilation? Maybe give a little definition of what a dilation is in your own words. Go ahead, pause the video, do it now, and when you're ready to continue, hit play, and we'll go through it together. So I came up with 3 possible different things you might have said. The first one says, a dilation is when an image has been zoomed in or zoomed out. Think of like the iPhone, or if on any smartphone or any tablet, if you zoom in, pinch and zoom, in and out, the 2 images are proportional. The second one says they are scale models of each other, which is true. A model race car and a real-life race car, all the proportions should be the same. It's just kind of an enlarged version of it. Third one says the images are the same, but different sizes. So they're the same shape, but different size, which is kind of the definition of what similar figures are. Similar figures are 2 figures with the same shape, but a different size. So that's what a dilation is. This has been lesson 3.1. Thank you for watching.